Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 11. Derivative Measurement. Capturing omega and k. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and the motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We are deep in the workshop of Book 10.2, Measurement Engineering. In our last session, we built the eyes, sensors that can see phi itself. But a single snapshot of phi is like a single frame of a movie. It tells us the shape, but not the story. Today, we learn to see the verbs. We learn to measure the very first derivatives of phi, the temporal rhythm omega, and the spatial pattern k. This is the skill of the Dynamist. You are entering the signal processing hub. Screens surround you, displaying streaming data. Not just numbers, but flowing fields. Your job is to extract the precise cadence and texture of change from this river of information, to separate the true signal of motion from the ever-present fog of noise. Scene: the ripple tank. Imagine a large, shallow tank of water. At one end, a metal bar vibrates up and down, driven by a motor at a precise frequency. Let's say 5 Hz. 5 times per second, it dips into the water. From this disturbance, ripples spread outward. They are clean, concentric circles moving away from the bar. We have our phi sensor, perhaps a high-speed camera looking down, using an interferometric setup to measure the water's surface height with phase precision. We get a movie, phi, x, y, t, a time series of phase maps. Look at a single pixel, a fixed point on the water. Plot phi at that point over time. You'll see an oscillation. The frequency of that oscillation is omega at that point. For a point directly in front of the bar, omega should be exactly 5 Hz, the driving frequency. Now look at a single frame, a snapshot in time. How is phi changing from one pixel to its neighbor? The direction and rate of that spatial change is the wave vector, k. For our circular ripples, k at any point should be a vector pointing radially outward from the source, perpendicular to the wave crests. Its magnitude, k, tells us how tightly packed the ripples are, the spatial frequency. This is our core puzzle. How do we reliably compute these derivatives, omega and k, from a noisy, sampled movie of phi? The derivatives are where noise gets amplified. A little fuzz in phi becomes wild fluctuations in its rate of change. Our challenge is to tame this amplification, to find the true motion beneath the static. The peril of the derivative, amplifying noise. Let's make the problem stark. The simplest way to estimate omega at a point is to take the difference in phi between two consecutive timeframes and divide by the time step. Omega is biting pretty much phi of t plus delta t minus phi of t over delta t. This is finite differencing. But our phi measurement has noise. Suppose at time t, noise makes phi read 0.1 radians too high. At time t plus delta t, noise makes it read 0.1 radians too low. The true phi didn't change, but our difference is minus 0.2 radians. Divided by small delta t, this produces a huge, spurious omega value. The derivative has turned a tiny, uncorrelated noise into a catastrophic error. Similarly for k. Calculating it via simple pixel-to-pixel differences, the spatial gradient, turns camera grain into a field of chaotic, meaningless vectors. The map of motion becomes a map of noise. So here is our first brutal insight. Measuring derivatives from noisy data is an act of controlled smoothing. We must suppress the noise without erasing the real signal. We must walk the tightrope between bias and variance. Variance, the random scatter in our estimates caused by noise. High variance means if you measure the same thing twice, you get very different answers. Bias, the systematic error caused by oversmoothing. If we average over too large a region or time window to kill noise, we might average away a real, localized feature. Our estimate becomes consistently wrong in a particular direction. Our entire craft is the management of this bias-variance trade-off, and we must quantify it. The coherence budget for derivative measurement. Before we compute a single derivative, we must assess our coherence budget. Do we have the capital to see motion clearly? 1. Temporal sampling budget for omega. The Nyquist-Shannon theorem gives us our first rule. To reliably measure a frequency omega, we must sample phi at a frame rate at least twice as high as omega. If our ripples oscillate at 5 Hz, we need a camera faster than 10 frames per second. Our budget rule: the sampling frequency must be 2 omega max. If we violate this, we get aliasing, high frequencies masquerading as low ones, a fatal incoherence. 2. Spatial sampling budget for K. Similarly, to resolve a spatial pattern with wave vector K, our camera pixels must be close enough together to see at least half a wavelength. Our budget rule: the pixel spacing must be pi hued K. 3. Signal to noise ratio, SNR. Budget in phi. This is our clarity capital. Noise in phi directly poisons derivatives. The rule is harsh. The uncertainty in a derivative scales as noise in phi by their sampling step. Smaller time steps, for higher temporal resolution, actually make omega noisier if the phi noise is constant. Our budget rule: for a target precision delta O or delta K, we require an SNR in phi that scales inversely with the sampling step. We need incredibly clean phi data to see fine derivatives. If our budget is insufficient, frame rate too low, pixels too big, phi too noisy, we cannot measure the true derivatives. We must earn capital, get a faster camera, a higher resolution sensor, or average more frames to clean up phi, though this costs us temporal resolution. Our coherence gate, after derivative estimation, is the dispersion relation check. This is beautiful and powerful. From episode 9, we know that in a coherent medium, omega and k stack are not independent. They are linked by a constraint clause called the dispersion relation. For our water ripples in the deep water limit, omega square ever k stack j star. For light in a vacuum, omega equals a c k star. Coherence criterion. In a region identified as a wave clause, the measured omega and k must satisfy the system's known dispersion relation within their error bars. This is a self-consistency test. If we measure omega and k in a ripple, and omega squared is not proportional to k star chase within uncertainty, then either 1. Our measurements are wrong, noise, bias. 2. The water is too shallow for the deep water relation. We use the wrong grammar. 3. The region is not a simple wave clause. Maybe it's a turbulent zone. The pass-fail rule. In coherent wave regions, the dispersion relation residual, the difference between the left and right sides of the equation, normalized by error, should be small. If it's large everywhere, our derivative measurement, or our understanding of the system's grammar, has failed. The dissonance indicator is specific. Estimates of omega or k that show pathological, unstructured flicker at the scale of the measurement noise. If your omega map looks like TV static, changing randomly from pixel to pixel and frame to frame with no smooth variation, you are almost certainly looking at noise amplified by an unstable derivative calculation. You have not found true dynamics. If coherence breaks, we stop. If coherence returns, we continue. If the dispersion relation fails in a region where it should hold, we cannot trust our omega and k fields. We stop using them for prediction or control. We must improve our measurement or our model. Regularization. The art of intelligent smoothing. So, how do we compute derivatives without drowning in noise? We use regularization. We introduce a gentle prior assumption. The true omega and k fields are smooth. They don't change arbitrarily fast over space and time. This is not cheating. It's using the grammar of coherence. In a physical system, omega and k are often continuous functions. A sudden pixel size jump in k is physically unlikely. It would require infinite energy. Techniques. For omega temporal, instead of just differencing two frames, we fit a smooth curve, a spline, a polynomial, a sinusoid, to the phi t history at each pixel over a short time window. The derivative of that fitted curve is our omega estimate. The width of the window is a regularization parameter. Wider window, more noise suppression, lower variance, but worse ability to track rapid changes, higher bias. Instead of taking pixel differences, we fit a smooth surface, a polynomial, a thin plate spline, to the phi of xy in a small neighborhood. The gradient of that fitted surface is our k estimate. The size of the neighborhood is the regularization parameter. The magic is in choosing these parameters. Too little smoothing, noise dominates, high variance. Too much smoothing, real features are blurred, high bias. We use cross-validation. We hide some of the data, fit our smooth model to the rest, and see how well it predicts the hidden data. We tune the regularization parameter to optimize this prediction. This is a data-driven way to find the sweet spot. The safety rail, quantifying the trade-off. Our safety rail is non-negotiable. Any reported omega or k field must come with an estimate of its resolution limit and its uncertainty. Resolution limit. This is the spatial or temporal scale below which our estimate is meaningless. It's determined by our regularization. If we use the 10 pixel neighborhood to estimate k, we cannot claim to see features smaller than 5 pixels across. We must state spatial resolution 5 pixels. If we use the 5-frame window for omega, our temporal resolution is 2.5 frames. We cannot see events faster than that. Uncertainty field. Just like with phi, we must produce maps of delta dota xy and delta k xy. These are computed by propagating the phi uncertainty through our regularized derivative algorithm. They will be large where phi was noisy and where the derivatives are intrinsically hard to estimate, for example, near defects. This rail prevents us from overinterpreting our results. It forces us to admit, here I can see the general flow direction, but here I can only say the flow is somewhere in this broad cone of possibilities. The triunity of the derivative. The derivatives omega and omega k are the perfect embodiment of triunity. They are the first shadows. Omega is the pure time echo, the rate of temporal change. K is the pure space echo, the pattern of spatial change. Together, they define the motion echo, the phased omega hood y k, the velocity at which the phase pattern itself moves. This is not the motion of stuff like water molecules, but the motion of information, of the shape. When we measure omega and k, we are not measuring two separate things. We are measuring the two inseparable faces of the first derivative of the one field, phi. They are a matched pair. Prediction spine, the hallmarks of good derivative estimation. Our methods yield a testable prediction spine. 1. As the signal-to-noise ratio in our phi measurements increases, the variance of our omega and k estimates will decrease as 1 over squared root of the SNR. The bias from our smoothing will remain constant at first, then eventually decrease as we can afford to use less aggressive regularization without being swamped by noise. 2. Method convergence. Omega and k estimates derived from independent methods should converge. For omega, compare the result from temporal curve fitting with the result from a completely different approach, like taking the Fourier transform of phi of t and finding the peak frequency. For k, compare spatial surface fitting with a phase shifting method, where we deliberately introduce a known shear in the image and see how the phase pattern shifts. As SNR improves, these independent estimates should agree within their combined uncertainties. 3. Phase velocity consistency. In a region we've identified as a wave clause, the calculated phase velocity, v is equal to omega score k h, should match a direct, independent measurement. How? Pick a specific phase value, say a wave crest in our movie, and track its position from frame to frame manually or with a correlation algorithm. That tracking speed should match v from our derived omega and k. Falsifiability, when dynamics defy description. Our falsifiability threads protect us from forcing a derivative story where none exists. If independent, well-founded methods yield persistently and significantly different omega fields that cannot be reconciled by honest error analysis, then the core assumption may be false. Perhaps there is not a single coherent phi field underlying these dynamics. The system might have multiple overlapping fields, or its behavior might be fundamentally stochastic in a way that cannot be described by smooth derivatives of a single potential. This would be a major discovery, forcing us to expand our ontological framework. If the estimated dispersion relation is violated everywhere in a system beyond all error margins, then the fundamental phi grammar we are using for that system is wrong. Our constraint clause library is missing the correct rule. We must go back to episode 9 style analysis to discover the true constraints governing this medium. Lanterns across scales, the universal need for dynamics. Measuring derivatives is how we understand change everywhere. Near-scale cardiology. An electrocardiogram, ECG, measures the electrical potential, a phi field, on the skin. The critical diagnostic information is in its derivatives, the slopes, k-like, and the intervals between peaks, omega-related. Ventricular fibrillation isn't just a weird shape, it's the loss of a coherent propagating derivative pattern, a traveling wave of depolarization, replaced by chaotic, high-frequency disorder derivatives. Weather prediction depends on measuring the spatial gradients, k, of pressure, geopotential height, a phi field, and the rates of change, omega, of temperature and humidity. The wind velocity is approximately proportional to the spatial gradient of pressure, the pressure gradient force. Meteorologists don't just look at pressure maps, they look at their derivatives, the tightly packed isobars that indicate a strong K, a steep gradient, and hence high winds. Far-scale cosmology. The expansion of the universe is measured by the redshift of light from galaxies. The redshift is a Doppler shift, a change in the temporal frequency omega of light. By measuring how omega changes with distance, a spatial gradient, a K-like concept, we derive the Hubble constant, the rate of expansion. We are measuring the derivative of the cosmic scale factor, a fundamental phi field of spacetime itself. In every case, the story is in the change. The noun is phi. The verbs are omega and chi. The ethics of derivative measurement, the danger of misplaced certainty. Here lies a subtle ethical pitfall, derivative hubris. Because derivatives feel like deeper truth, there's a temptation to present omega and chi maps as revelations while downplaying their massive uncertainties. This is catastrophic for engineering. If you design a control system based on a key field that you present as precise, but which in reality has huge error bars in key regions, your system will fail. It will try to align with a phantom flow. In medical imaging, misestimating the velocity, a derivative, of blood flow could lead to a missed stenosis or a false aneurysm diagnosis. The safety rail of reporting resolution limits and uncertainty fields is an ethical mandate. It is the duty of the dynamist to say, I can see the general trend here, but I cannot tell you the exact value at this specific point. Any action based on such specificity is on you. Power without coherence is self-destruction. And coherence in dynamics begins with humble, honest accounting of what we can and cannot see of change. A measurement scene, the water ripple tank. Let's enact our roadmap's measurement scene. Scene, the water tank with the vibrating bar at 5 Hz. What we measure. A high-speed phi of XYT movie from our interferometric sensor. The pass. We process the movie. Our algorithm produces an omega of XY map. It shows a uniform 5 Hz across the entire tank where ripples are present, with small error bars. The KXY map shows beautiful vectors pointing radially outward from the bar, like a sunburst. The vectors are longer closer to the bar, tight ripples, large K, and shorter farther away, spread out ripples, small k. We compute the phase velocity omega xk. It matches the known speed of surface waves for the water depth. We try a different method for k, phase shifting, and it gives essentially the same vector field. The dispersion relation check passes beautifully. The omega map is a patchwork of random numbers between 0 and 10 Hz. The key map is a chaotic swirl with no relation to the source. The two methods for key disagree completely. The phase velocity calculation produces nonsense numbers. The dispersion relation is violated everywhere. This indicates our phi data is too noisy, our frame rate is too low, aliasing, or our derivative algorithms are unstable and unregularized. We have not captured the dynamics. The recognition skill, seeing the need for derivatives. You know you need this skill when you look at a phi movie and ask, how fast is that moving? Or, in what direction is that changing? The moment you move from describing what is to describing how it changes, you have entered the domain of derivative measurement. If you find yourself wanting to draw arrows on a map to indicate flow or quote a frequency, you are thinking like a dynamist. The digital twin, the dynamic sandbox. Our twin is now a derivative testing ground. We use it to generate perfect phi movies with known ground truth omega and k fields. We then add realistic noise, shot noise, vibration blur. We run our derivative estimation algorithms on this synthetic data. We can see exactly where they fail, how the bias-variance trade-off plays out, and how to set our regularization parameters optimally. We can test the limits. How noisy can phi be before we lose all hope of estimating k? The twin provides the answer key against which we hone our craft. Enabling the future, the path to control. This skill, derivative measurement, depends on clean phi maps, an understanding of constraint clauses like dispersion relations, and good sensors. It enables the next critical steps in our journey. Topological detection. Defects are singularities in the key field. To find them, you need a robust key map. They are where the smooth derivative story breaks down in a specific integer way. Control theory. You cannot control what you cannot measure. Feedback control relies on measuring not just the state, but its rate of change. To stabilize an unstable pattern, you need to sense how it's beginning to deviate, which is a derivative. To guide a moving defect, you need to know its velocity, which comes from omega and k. Dynamics require knowing derivatives. This part provides the eyes to see those dynamics. Zenodo and the calculus of noise. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. The papers will formalize the regularization techniques, Tikhonov regularization, total variation regularization. They will present the equations for propagating uncertainty through these schemes, giving explicit formulas for delta deca and delta k double star as functions of delta phi and the regularization parameters. They will derive the Cramer-Rao bounds for derivative estimation, the fundamental limits of how well you can know omega and delta k given noisy phi data. This is the rigorous mathematical backbone of our craft. Return to the phi. Let us zoom out. We have moved from seeing the static landscape of phi to seeing its winds and currents, its omega and delta k. We have learned that this requires not just computation, but careful, honest regularization. We must smooth, but we must know how much we have smoothed, and we must report the limits of our vision. We remember, there is only one field. Its first derivatives are the twin faces of its most basic change. Measuring them is how we begin to understand the plot of the universe's story. Our maps of omega and k are the first sketches of causality in the phi language. We have added a crucial discipline, the explicit management of the bias-variance trade-off and the mandatory reporting of resolution limits. We do not present omniscient vector fields. We present our best bounded estimate of the flow phase. This is the foundation for interacting with the moving world. You cannot catch a ball if you cannot see its velocity. Closing. So picture yourself in the signal processing hub. On one screen, the raw phi movie plays, the shimmering water surface. On another, Your algorithm outputs its results in real time. A map of color shows omega. Cool blue for slow, warm red for fast. Overlaid are slender arrows showing K, like grass bending in the wind. A sidebar shows the confidence. Temporal resolution 0.1 seconds. Spatial resolution 2 millimeters. Dispersion relation residual 0.05. Pass. You are not just watching pretty ripples. You are quantifying their essence, their rhythm, their direction, their speed. You have just learned to see the verbs of the phase field. This is part 10.2.2, derivative measurement, capturing omega and k. It is the second branch of book 10.2, measurement engineering, giving motion to our vision. In our next session, we will use this ability to find the punctuation marks in the phase story. We will learn to detect topological defects, the vortices, the singularities, where the smooth derivative narrative breaks down in a profound integer way. We will learn to see the knots in the tapestry. Remember, one field, phi, with its infinite echoes in time, space, and motion. We can now see not just the field, but its flow. Our perception deepens. We are learning to read the universe's poetry, line by moving line. Salam and peace be upon you.